Okay, this is the standard Norman window problem where we have a semicircle placed on top of a rectangle. We've got 28 feet of material for the outside or the perimeter of the window. And we want to know what dimensions should we have to maximize the area, the amount of sunlight that comes through that window. First thing we want to do is maybe get a formula for L in terms of R. By the way, P is just a constant. It's this 28. So if you wanted to replace P with 28 and all the equations that appear on this board, you could do that. But this is a more general answer. So the perimeter is, well, this is a semicircle. The circumference of a circle is 2 pi r. So for a semicircle, it's just pi r. And then for this rectangle, we're only looking at the outside perimeter. So we're not including this length of the rectangle in the perimeter. It's just 2L plus 2Rs. And so if we solve that for L, there's a formula for L in terms of R, where again, this P is understood to be a 28. So a formula for the area of the Norman window is the area of the semicircle, which the area of a circle is pi r squared. So we take half of that to get the area of the semicircle. And then the area of this rectangle is 2r times L, length times width. So here's 2r, but I've replaced L with this expression right here. So we have a function of the area depending only on r. And if I distribute this 2r, these 2's cancel out, and I get r times p, or p times r, minus pi r squared minus 2r squared. So there's your formula for the area in terms of the radius. And if we take the derivative of that with respect to r, set it equal to 0, we'll find a critical number for the function. So the derivative of this first term is pi r. The derivative of pr with respect to r, p is a constant, is just p minus 2 pi r minus 4r. There's your derivative. And while we're at it, I'll take the second derivative. We'll see how we're going to use that in a second. So if we set this equal to 0, which I've done here, and solve for r, we get all the terms containing r on one side. 2 pi r minus pi r is just 1 pi r. Factor out the r, we get pi plus 4. Divide both sides by pi plus 4, and there's your formula for r in terms of p. That's the radius that we think is going to give us the maximum area. If I look at the second derivative, you can see the second derivative is always negative, so it's always concave downward, which means this value of r, p over pi plus 4, is where the tangent line is horizontal. It's giving us a maximum area. Okay, so 28 over pi plus 4 would be an exact answer for this problem. There's a decimal approximation. To get L, you have to plug p over pi plus 4 into this formula. We'll leave that to the viewer. Okay, there you go. Hope that helped. If you have any questions, post a comment.